So hello everyone, good afternoon. So welcome back to our new session on Hexagon architecture. And today our speaker is Abhikrant, and he's currently working as a member of AI compiler team at Qualcomm, software engineer for 10 years of experience spanning across design and development of compilers, device driver, and firmware. His interests include high performance computing, optimal edge processing, and compilers to augment performance. So now, Abhikrant, you
Uh,
can continue your talk. Yeah.
Thank you so much, Avnish. Yeah, uh, and thank you, sir, for giving me this opportunity to present here. A few things that I wanted to mention is like if you have any questions, please feel free to ask them on the go itself. I would like this session to be as interactive and as informative as possible, and I would like to explain as many details of Hexagon architecture as possible in this session. So to all the attendees, please feel free to interrupt me whenever you have any questions. So yeah, today's session will be about Hexagon DSP, the architecture of Hexagon DSP, how the vector engine in Hexagon DSP is helping multiple camera, imaging, computer vision, and machine learning applications in real world mobile phones that we have in our hands today. So what you see on the screen right now is the Snapdragon 820 architecture, the chipset architecture. Uh, so there are multiple processors that are available in the Snapdragon 820 chipset. The main or the main brain of the chipset is called the application processor, which is also known as the complex CPU. This CPU is responsible for doing all the control operations, or all the control code gets executed over here. This is predominantly based on the ARM architecture from the company ARM, and Qualcomm licenses this from ARM. There's another processor which is dedicated for graphics processing, and it is called Adreno, which is highlighted over here. The job of Adreno architecture is the job of Adreno GPU is to ensure optimal performance when we are playing games at high FPS. It also helps in graphics rendering for multiple other applications. Apart from the CPU and the GPU, DSP is a key component in the Hexagon SoC. SoC stands for System on Chip, and that's another terminology, or it's a similar term as as chipset. So I will continue to use SoC as a term going forward in my presentation. So on the SoC, Hexagon DSP plays a very, very important role. There are multiple Hexagon DSPs that are present, uh, and all of them have some specific work to be done. So one of the DSPs, Hexagon DSP, that is responsible for all compute-related operations is called the Compute DSP. And this is mainly used for audio, mainly multimedia applications like audio, voice, image processing, any kind of video processing, or computer vision kind of applications. Yeah, sorry about that. Um, so the compute DSP's main brain, or the main horsepower is gained for all these applications is gained through a specific vector engine or a vector coprocessor, which is known as HVX. It stands for Hexagon Vector Extensions, and it is a coprocessor to the DSP along with the scalar hardware that is present. So I'll talk about this in the subsequent slides as we move forward. Apart from the compute DSP, there's another Hexagon DSP that is dedicated for modem processing, and this modem processor or modem DSP is responsible for all our communications from the phone to the network, which include like 4G or 5G communication, carrier aggregation. All these are handled by the modem DSP, which is again it's a different version of Hexagon DSP. Apart from the DSPs that I mentioned over here, there's one more DSP that is meant for sensors, and that's like an always-on chip. It is powered on throughout the life cycle of the phone, and it's mainly used for any kind of sensor processing, like your gyrometer or a GPS sensor. All these use sensors low power island, which is again a Hexagon DSP. So apart from these three DSPs, there are dedicated hardwares for doing multimedia processing. There is a dedicated hardware to do video playback, broadcast, streaming, and conferencing. There is a dedicated imaging hardware called as ISP, image signal processor. And there's a dedicated hardware for doing all display related processing, like for Wi-Fi display or wireless display. There are some other components in the SoC which are responsible to ensure that the memory accesses are protected by specific permissions, and that is what is handled by this system security layer in the SoC. And apart from all these processors which I mentioned, there are dedicated memory regions. There are caches. There are memory management units. You will have a dedicated RAM, which is also called as DDR, and there'll be a controller corresponding to this. So all these things, when clubbed together, they form a chipset. So any questions on this? Okay, sounds good. So now we'll take a deep dive on the Hexagon architecture, and more like predominantly we'll be discussing about the vector engine that is present on Hexagon. The vector engine on Hexagon is called HVX, which stands for Hexagon Vector Extensions. Now these are DSP extensions that are meant for imaging, computer vision, and machine learning applications. And these find use cases, like almost all the use cases on the smartphone related to imaging and computer vision and machine learning are mostly running on HVX. We have camera applications using HVX. The XR, or the metaverse as it is referred today, it makes use of HVX heavily. A lot of algorithms are powered by HVX. A lot of head-mounted displays make use of algorithms that run on HVX. We have computer vision library that Qualcomm ships out. It's called FastCV library, and it is similar to the OpenCV library that we have in the open source world. So the FastCV library has the APIs for doing computer vision, for running computer vision algorithms, hand optimized to be executed on HVX. And last but not the least, we have video applications that again make use of HVX. Now, the reason why all these applications are running on HVX is because all these applications are firstly, they are computationally very, very expensive. They require a lot of memory bandwidth. They require a lot of computation power. And along with like both these things, they come at a very premium cost, which is the cost of battery power. So HVX is very highly optimized to get better performance for every megawatt of energy that is spent. And this turns out to be substantially better than a traditional CPU or the ARM processor that we have on the SoC. So that is why there are a lot of applications running on the mobile phone that can be run in the always on mode, and still they would not drain out the battery significantly. And I have some slides in the subsequent part of my presentation, which will explain like why the performance is better on HVX when we compare it with the ARM architecture or a quad core ARM CPU. So this is like one of a real world algorithm, which basically improves the low light performance of photos and videos. And this is one of the algorithms that the camera pipeline is using. And this is accelerated on HVX. The algorithm is responsible for reducing the local tone mapping. It improves the local tone mapping, and it reduces the temporal noise, which is introduced by the lighting in low light scenarios. And what this eventually does is it adaptively brightens the image, and it reduces the dark areas of all the videos and images. And this is actually running on HVX, this algorithm. Another interesting algorithm that runs on HVX in real time right now is adaptive detail enhancement. So on the left side, you can see like the original image, which does not have very sharp features of the object of interest. But when we use the adaptive detail enhancement algorithm, it runs a bunch of filters on the whole image, and it tries to enhance the features of the image. And again, this is processing that is done on HVX. So yeah, I think we've seen some use cases that HVX uses. Now we'll do a deep dive into the architecture of HVX. So we'll be covering like three major aspects with respect to the HVX hardware. We will understand about the domain-specific architecture of HVX and why it is so suited for specific domains like image processing, machine learning, and computer vision. We'll also talk about the familiar programming model that Hexagon has to offer. What are the different tools that are available that augment the performance of algorithms on the SoC or on the hardware? And it also helps like end programmers use HVX in a much more simplified manner. And in the end, we will also discuss about some system integrated features that are available, which allow the data from the camera hardware to be read directly into the HVX hardware. So yeah, the first part of the HVX architecture that I want to discuss is the Simdi extensions. For those of you who are not aware of what SIMD is, SIMD stands for Single Instruction Multiple Data. Now, HVX has very large SIMD extensions. By that, what I mean, you can process 1024 bytes of data in a single instruction of HVX. And apart from 1024 bytes of SIMD, there are 4 vector hardware slots that are available to process 4 HVX instructions in parallel, which is also known as VLIW, or very long instruction word. Now, what this augments or what this helps us with is we are able to process 4096 bits of data in a single cycle. And that is pretty huge amount of data for a single cycle of the oscillator. Now, since we have a SIMD or one vector of HVX can process 1024 bytes of data, we can actually perform 256 8-bit by 8-bit multiply operations, or we can perform 64 16-bit by 16-bit multiply operations. Now, these can be in the form of character or int8, or in the form of int16 or unsigned int16 multiplications. And this is done in one of the instructions. This is possible in one of the instructions. When we execute this across 4 vector hardware slots, we get 4 times the performance of this 256 into 8 cross 8 multiply, or 64 16 cross 16 multiply operations. Now, the hardware has 32 vector registers. Now, all these registers can again store 1024 bits of data. And there are different modes to access this data. Right now, HVX has support for only fixed point arithmetic. So there is support for int8, 16-bit integer arithmetic, or 32-bit integer arithmetic. There is no support of floating point added in HVX right now. And the reason for that is that most of the computer vision and imaging applications, their algorithmically, they work really well with fixed point arithmetic. And one obvious advantage that we get with this is by not introducing floating point hardware in HVX is that the size of the coprocessor reduces significantly on the die, and it also reduces the energy consumption of the hardware. So there are special instructions in the HVX instruction set ISA. There are special instructions which help operations like convolution, which need sliding window operation. There are dedicated instructions which help in getting data from lookup tables. And histograms is a very important metric that is used in computer vision to extract meaningful information from an image. So there are like direct instructions that are added into the HVX ISA so that we can get meaningful information for imaging related applications. And that is one of the primary reasons why we call it like a domain specific architecture. It is very much suited for image processing kind of applications. So on the right side, we have like an example of how a multiplication and accumulation operation takes place. So the example shows multiplication of a HVX vector with a scalar value. And the scalar value is multiplied, and then it is accumulated into a single value. By accumulation, I mean it is an addition operation. And once the addition operation happens, the data is again stored back into a specific vector, into an output vector. Now, this whole operation of 1024 bytes takes place in a single instruction, and that is what leads to better performance of many imaging applications which have high bandwidth and computational power requirements. So, like, this is again slightly older data that we have, but the performance based on the hardware architecture that we have, it is sufficient for ultra HD video post processing of a 20 megapixel camera burst. So it can do like real-time processing of 20 megapixels of ultra HD video. This has obviously improved over the years significantly as the architecture has evolved, and now we are able to support even HD and 8K video processing at very high megapixel rates. Yeah. So now we'll talk about the multi-threading model, and we often call it internally in Qualcomm as thread level parallelism. What this thread level parallelism does is it allows multi-threading of applications across scalar and the vector hardware, and it allows coexistence of scalar applications that want to make use of the scalar hardware and the vector hardware. So if you would have remembered in the previous slide, I mentioned that there is a vector unit that has like 4 slots which can process four vector units simultaneously. So this is like, this whole thing is called an HVX context. And an HVX context comprises of 4 HVX, 4 vector slots, which can process 4 instructions in a single cycle. And we have 2 such HVX contexts on the Snapdragon 820 SoC. Now, if we talk about the scalar version of the Hexagon, there are 4 dedicated scalar hardware threads that are available on Hexagon. And these scalar threads are again responsible for processing the scalar instructions that we have. But again, the point of scalar instructions is that, like, the advantage of scalar instructions, or the reason why scalar instructions exist, is there are some applications that need floating point processing. So that is the advantage of scalar instructions, or the reason why we have them. But the disadvantage with scalar hardware is that it can process only 32-bit of data in a single instruction. So you get 32 into 4, which is like 128 bits of data gets processed in one particular slot or in one particular cycle of the instruction. So there are 4 parallel scalar threads that are available, and each thread is having its 4-way VLIW architecture. All these 4 threads have shared access to the L1 data cache and the L1 instruction cache, and the L1 caches, respective caches, are in turn connected to the bigger shared L2 cache memory. Now, when we have 2 HVX contexts, these can be controlled through any of the 2 hardware threads. So in this image, if you can see, one vector HVX context can be mapped to one of the scalar or one of the hardware threads, and this particular vector context can be mapped to this hardware thread. Now, what this gives us is still there are 2 threads that are left for performing some operation, and hence some scalar applications can be executed on these 2 threads, hence allowing the coexistence of vector as well as scalar applications to coexist at the same time. And one more thing that I want to highlight over here. So each thread gets like 500 megahertz of clock. Now, if we take into account 2 HVX contexts, we get a total of 1 gigahertz of performance, total vector performance from the HVX engine. And if you see, like, as I mentioned earlier, in one cycle, we can process 4096 bytes of memory. So for 2 HVX contexts in one cycle, we can process 8192 bytes of memory. Now, if you scale it to 1 gigahertz of performance or 1 gigahertz of clock cycles, you can automatically think how much of a performance advantage we have with the HVX architecture. And that being said, there are still 2 scalar threads that are available. which can perform scalar processing. And this is why we call this whole threading model as thread level parallelism, because it augments parallelism in multiple ways, and it allows coexistence of scalar and vector threads. Another important aspect of the HVX architecture is the memory and how we've set up the memory in the processor. So if you see, like, L2 is the first level of memory over here for the vector units. So the vector units are not connected to L1 cache. The vector units are only connected to the L2 cache directly. And this is different from the scalar architecture. Scalar architecture has access to L1 cache, but that's not the case for the L2 cache. And this is mainly done because the domain for which vector hardware was introduced was imaging, and all imaging applications, like, they need more memory to be available, and hence the L2 cache size has been increased over the years. And since more data from DDR can be prefetched into L2 cache because of its bigger size, directly we connect L2 cache to the vector registers, and that's why there's no need to introduce like a smaller L1 cache in between. Now, the advantage with this is that in an ideal scenario, like where there are no cache misses, there is like a single cycle load to use that happens, or load to use kind of a programming model that is supported. And this also augments full bandwidth or full usage of the HVX vectors. And this is with the assumption that there are no cache misses that happen, and the data is already available in the cache. I mean, when cache misses happen, obviously that will lead to stalls, and those stalls need to again wait for the data to be available, to be read from the DDR memory, and that will take some cycles. But in an ideal scenario where there are no cache misses, like, we can make use of the full bandwidth that the data bus has to offer to transfer data from DDR memory to L2 cache memory. One more thing that the hardware takes care of is that the L1 and L2 are kept as hardware coherent, which means that for a programmer, there is no need to invalidate and flush the cache. That will be taken care of by the hardware itself. The vector units also support variety of load and store operations. Like, you can also perform unaligned loads, but in an ideal scenario, if it's an unaligned address, then it has to align it appropriately and then load the data into the vector registers. And the hardware also supports per byte conditional loads and store operations, which means that if a user is not interested in loading or storing of 1024 bytes in a sequence, then there are ways to mask some of the bits in the vector or some of the elements in the vector and load data conditionally from the memory into the vectors for further processing. Any questions?
Hello.
Yeah.
I have two questions. Basically, it's just one question that, like, keeping the hardware coherence between the level of caches and also along an unaligned memory, etc. Like, as far as I know, those lead to, let's say, those lead to, let's say, higher access times for, like, those lead to more complexity and, like, higher, lesser performance. So how was that, like, I don't
I
know
think
if I'm making.
no. I think so. Let me understand the question. You're saying, like, if L1, if the caches are kept as hardware coherent, then it can lead to degraded performance because of the cache misses, right?
Yes.
Yeah, I think that is true. I mean, one of the reasons why we skipped out L1 data cache was because of this, because L1 data cache was responsible for a lot of cache misses. But that being said, L2 also has cache misses. So the recommended approach to avoid this is to do a prefetching of data before we actually need it. And that helps in ensuring that the data is available when the processor actually needs it, and there are no stalls that happen in the hardware. That being said, there is one more interesting feature that the hardware supports. Let's say if your so in the previous slide, I mentioned that all 4 hardware threads have 500 megahertz of frequency, and thus giving like 2 gigahertz of processor, uh, like the clock. Now, the interesting thing is, like, let's say if this hardware thread is stalled, those 500 megahertz that of clock that is being occupied by this particular hardware thread, in case of a stall, the clock will get split across these 3 hardware threads. And once the data is available for processing on this particular stall, that's when the hardware will have the ability to reclaim, the hardware thread will have the ability to reclaim that particular clock, which it is supposed to have. So there are few things that are done in the hardware to avoid the problems of whenever there is like a cache miss. Like, one thing is to get rid of the L1 data cache from the vector hardware, and the second is to, if a stall is seen across any of the hardware thread, we don't allocate any clock to that particular hardware thread. Instead, it gets distributed across the other threads until the data is available for usage. So that helps in ensuring that the data is available, and we don't lead to stalling of the processor. I will actually
All
talk
right.
about this. Yeah, I will talk
Okay.
about this concept in the future slides. But yeah, I thought I'll probably discuss now that you asked it.
Okay, and another I have is that like unaligned, like for example, in on x86, all vector instructions they require aligned memory accesses because they because that's how they would gain performance. So why does this architecture allow like unaligned memory accesses for vector units?
I think what you're saying is absolutely true. In an ideal scenario, we would want aligned addresses to be fed to the processor, but not all programmers are aware of that. So that is the only reason why unaligned access is supported, because we have seen in the past, like, a lot of programmers are not aware of the aligned addresses or the alignment to which they need to adhere. And because of that, it leads to invalid data being picked up from the DDR memory, and in turn it giving incorrect results. So that is one of the reasons why we have unaligned addresses. That being said, unaligned loads. That being said, it is obviously less performant when we compare to aligned loads, because the processor needs to back align to an aligned address, load the data, and then like in an unaligned load or store operation, 2 vectors will be used. So when 2 vectors are being used, it will obviously be bad in performance when we compare it to a aligned load or store.
Okay, so is there like a fast path for if you have an if you have an aligned memory access?
Sorry, could you please pardon?
Yes, let's say there's do you kind of like short circuit if there's an aligned memory access to like make that case faster, or like would it be the same speed for whether it's aligned or unaligned memory access?
No, aligned accesses will be faster, definitely. Unaligned will be slower, because in general, like, 2 vectors will be involved. We will have to load 2 vectors amount of data, and then like store that into a separate vector. So there is some work that is involved by the processor. Like, there are dedicated instructions to take care of that. So an end user does not need to worry until they're using the correct set of instructions. But if you compare its performance, it can like it can have like not the most optimal performance.
All right, thanks.
Yeah, sure. So yeah, I think in the previous section we discussed about the domain specific architecture and how that helps mostly in the imaging related applications. Another aspect that I want to cover in this presentation is regarding the familiar programming model of HVX. and how we have different tools that are available that help an end programmer use Hexagon in a relatively seamless manner. So the first thing that I want to compare here is that the DSP with HVX has a CPU-like programming model. And for our comparison over here, we have used the quad-core ARM CPU, which has a vector architecture of Neon. Neon is the vector architecture of ARM that ARM it provides. So that is what we are using for any discussions going forward in this presentation. The results or the benchmarks that we'll be using in the subsequent slides will also be in comparison to a quad-core ARM CPU with Neon architecture. And the comparison will be done with the Hexagon DSP, which has the vector extensions. So talking about the CPU-like programming model, there are a lot of similarities that Hexagon has with the CPU. There is support for multi-threaded programming with cache-based coherency. There are SIMD instructions that are available for vector hardware. There are scalar instructions for the scalar processing. And then there is, as I showed you, that both CPU and DSP, they support a mixed kind of or coexistence of vector and scalar processing. So these are like some features that Hexagon has similar to any CPU. But there are some advantages or key differences with respect to performance and power that the DSP has over the CPU. The first advantage is that the SIMD pipeline or the SIMD, the size of the vector on Neon architecture is just 128-bit, whereas on Hexagon it supports 1024 bits of data in a single vector. And on top of that, there are 4 hardware slots to process 4 instructions in a single hardware, in a single HVX context. So you get like 4096 bits of data to be processed in a single instruction. Now this gives like 8 times the computational power of the Neon architecture. The second advantage of Hexagon DSP over CPU is that the L1 cache on Neon is just 32 KB, whereas SIMD threads share a 512 KB of L1 and L2 caches. So this again gives like 8 times more efficient data sharing between the different threads. And since the data is available for imaging applications in a larger memory pool, this helps in the image processing kind of applications significantly. Yeah, this is like debatable, the third point. Like there is floating point support available in SIMD of Neon, but Hexagon has only fixed point support available. This is again done by choice for imaging kind of applications because they do well with fixed point arithmetic. And what this helps us with is that there is low area needed for the chipset on the die. And this obviously reduces the power requirements because there is no need of supporting floating point arithmetic on the hardware. So as you can see, it's evident in this diagram also. For Neon architecture, one thread is doing 128 bits of processing. Whereas over here, you can clearly see that one thread is doing like 4096 bytes of processing. And this is what helps in improving the performance of the algorithms on the DSP. The DSP also has a very, very familiar programming model. There are a lot of conventional tools like GCC, G++ that are supported on the DSP. Now, most of the people are moving towards Clang, which is based on LLVM compilers. So the DSP supports LLVM compiler and all the associated tools with it. There is a dedicated debugger. There are tools to do multiple operations like reading the ELF file or doing name mangling. All these tools that are available in the open source LLVM community, those are supported by those are supported for Hexagon DSP also. The RTOS that runs on DSP, it's called CURT. CURT supports POSIX-like threads, so you can easily use your pthread APIs to start a thread, to join a thread, all the APIs like pthread join, pthread create, and pthread kill can be easily used on the DSP because they are supported by the DSP RTOS. Because we are using LLVM compiler to generate code for the DSP, there is an easy or a very seamless support of C++ and C programming language features. And another advantage of using C and C++ is that Hexagon intrinsics, which are available in the programmer's reference manual, those can be directly used in our C and C++ code. Along with all these features that I mentioned above, there are some pre-optimized mathematical libraries and computer vision libraries. And even we have like SNP library, which is for machine learning algorithms. So there are some pre-optimized libraries which have hand-optimized kernels for HVX execution, and these are free to be used by our programmers. And these are available on developer.qualcomm.com website for usage. And these come in the form of an SDK also. These come along with the Hexagon SDK also, for which there will be another session in the upcoming days. So that will cover, I think, more details about what are the pre-optimized libraries available. Now, apart from the tools and techniques that are available, there is support for offloading. I'm sorry, could you please mute your mic? I think I heard somebody's phone.
Hello?
Thank you.
Please continue. I think there was someone.
Yeah. So I would like to emphasize that apart from the conventional tools and techniques, there is support for offloading the processes from the ARM processor to the DSP. And this is done through a driver that we have, which is called FastRPC. And FastRPC stands for Fast Remote Procedural Call. Now, what FastRPC allows us to do is that it allows DSP code to be dynamically loaded from a shared object on the HLOS, and then map that particular shared object with the DSP memory, perform the processing on the DSP, and then return back the results to the HLOS or the apps processor. Now, with the advantage of having the ability to get data on the HLOS or on the Android, on the apps processor, we are able to support high-level Android framework APIs that are available in the Android SDK or the Android NDK. So if you would have seen any Android documentation, there are dedicated APIs available to make use of the camera, video, voice call, audio call. There are different APIs that support all these functionalities. Now, Qualcomm has done or has added support for all these pre-processing APIs in real time to be supported from the Android HLOS. And what this does is, if there's a high-end application developer or a top level application developer who is developing an Android application, if they make use of the Java APIs, which make use of the camera pre-processing pipeline, they will be able to make use of the DSP because of the work that is done by the Qualcomm's like camera team. And this is again helpful, or this is done because of, this is possible because we have FastRPC remote procedural call driver available, which allows very easy and like very easy communication between the HLOS, that is the apps processor, and the DSP. I think this will also get covered in the subsequent session on Hexagon SDK. So yeah, you should get more details on FastRPC and how the DSP offloading works from Android. So in case you don't understand it right now, please come back for the next session that we have planned for Hexagon SDK, and there all these concepts will be discussed in a much more detail, and there you will be able to understand them really well. There's one more session that we have planned, which is on halide language for HVX. So over the past few years, we have been developing halide language, which is again a domain-specific language for image processing applications. And there's a dedicated session for halide on HVX, which will be taken by Suyog, who is my colleague here at Qualcomm. So overall, like there are a lot of tools. There is support from the device driver side, and there are like high-level application, high-level languages that are available, which help an end user to use HVX in a very seamless manner, so that it is easy for end users to develop applications and make use of the power and the performance that HVX brings with it due to its sophisticated architecture. So yeah, I think we discussed two very critical aspects about the architecture and the familiar programming model. Now we will talk about the camera side tight system integration that HVX has to offer. And this is going to be like pretty interesting because it's something from the industry use case perspective, very important.
Sorry to interrupt, but I have a question.
Oh yeah, sure.
On the previous offloading that you were talking about. So is the not this, the previous slide. So yeah, you mentioned EC DSP offload from Android. So can you help me understand what a general flow is like? So is this offloading the only way the DSP is ever invoked, or is it is it like there are certain flows in which the DSP is by default used, and this is something that is extra from that?
So I think both the things are possible. You can write your application and completely on the DSP and run it on the DSP. A one-time invocation would be needed from the apps processor because that is the master processor. So any process, like any application that has to interact with the DSP, like DSP is kind of a slave processor in a master-slave configuration, and apps processor is the master processor. So the start of any process has to happen from the HLOS or high-level operating system or the apps processor. But that being said, we have a lot of use cases where we just make like one entry call to the DSP, and then the DSP is aware of what needs to be done, and everything. By everything, I mean the whole processing happens on the DSP, and the results are only shared back to the apps processor. The processing is not done on the apps processor because of the high power and low performance that it offers.
Right. So when you call not just this, but any DSP programmable, you basically say that you insert some, I don't know, like code that you know that is going to be the primary use case of the DSP, and put it in there, and just, as you mentioned, use the entry points, right? Is that how generally DSPs work?
Right. At least in this case, the Hexagon DSP works in the same way, yes.
Right. And what is a use case for this offloading?
A lot of use cases, like most of the camera applications that you see being used, like a very simple example is when you talk about, let's say, panorama. When you take panorama from your camera, it's like a high-level application, right? It's visible on your phone screen, but eventually it is communicating to the JNI Java layer of Android. The Java Android layer is communicating with the native layer of the Android HLOS. That HLOS or the native layer is in turn communicating with the DSP to actually do the processing and stitching of the images, ensuring that the ghost images are removed in the panorama that gets generated, and eventually give like a stitched image, which is the panoramic view of whatever the user wants to capture. So that is like one end use case with respect to camera. But there are a lot of other use cases, like the video processing is like video post processing. There are a lot of algorithms that run on the DSP, which run in the similar fashion. Like you just press the button on to start recording your video on the phone screen. It interacts with the JNI layer, which in turn interacts with the NDK. And eventually it goes down to the DSP for doing any kind of video post-processing or pre-processing.
Right, but so how is it decided whether to have it, forgive my terminology if it is wrong, but how is it decided to have it as a native DSP instruction, or is it, or to offload it at on the fly?
That control code, I think, yeah, some programmer needs to do that. That there is like a control code. So as I mentioned, that the apps processor is the master processor to initiate any communication to the DSP. So the camera team in Qualcomm takes care of writing that control code, which gives that decision power of whether the whole application needs to run natively or it needs to get offloaded to the DSP.
Right. Okay. Cool. Understood. Thanks.
Yeah. Any more questions? Okay. Thank you. So yeah, I think we'll talk about a very interesting use case with respect to the camera pipeline that is available on the whole Snapdragon SoC, and a lot of components are interacting, and how HVX is playing a very important role in this. So if you see the area that is highlighted in yellow, this is what comprises of the streaming interface or the camera streaming interface. So the data from the camera sensor can be directly fed into the L2 cache of the DSP. Okay, there is no need to store the data from the camera sensor to the DDR. There are multiple reasons for this, but mainly the power that is needed in storing the data to the DDR and then again fetching the data to do post processing is significantly higher. So that's why the camera sensor data is directly streamed into the L2 cache, and this is like raw data. So certain things that the streamer does is it can stream up to 1.2 gigapixels of data in every second. So that's like a huge amount of data that comes into the L2 cache. And one more thing that happens is that the streamer is responsible for ensuring that the format is appropriate padding is applied, the alignment, as I mentioned, that the memory allocated for the buffers that are transferring data to the L2 cache, they need to be aligned. Only then the processing will be optimal. So all the aligned loads or the aligned memory buffer allocation is ensured by the streamer hardware. And the data, when it is passed towards the DSP or from the DSP back to the camera ISP, this whole operation is done in circular buffers. So there will be circular buffers that keep passing capturing the data from the camera sensor, sending it to the DSP, and DSP, once the processing is done, it will send the data to the camera image sensing processor. Now this synchronization is handled through something called as memory mapped control registers. So there are dedicated control registers which can be programmed in such a way that they allow the whole system to understand how the data needs to be transferred to and from. And this is like a very important feature for, it is a very important system level feature which ensures that the performance is maximum, and at the same time the power consumption is as minimal as possible, because we are not storing data into the DDR memory, as that is extremely expensive. Any questions on this? Okay. The next system level feature that I want to talk about is, it's called SMMU, which stands for Shared Memory Mapping Unit. So we have for Hexagon DSP, there is a shared memory mapping unit, which allows for zero copy data sharing with the CPU. And what this means is there is support for ensuring that there are as less cache misses and cache the cache hit is as much as good as possible, and there is zero overhead in ensuring that the data is gets mapped to the memory of the respective processor instead of actually copying the data over to the respective memory. So because of this SMMU feature, multi-threaded DSP can service multiple applications simultaneously, which basically means that there is a concept of context bank in SMMU. SMMU has multiple context banks which are allocated to every application. Now, because there are different context banks allocated for every application, you can think of context bank as like a memory region in the DDR, which is allocated to a specific application. So what happens is like audio applications will have their own context bank, camera applications will have their own context bank, and computer vision applications will have their own specific context bank. Now, because there are specific context banks available in the DDR memory region, SMMU will allocate memory in those specific context banks based on the application of interest. Now, what this does is like it allows multi-threaded DSP to service multiple offload sessions simultaneously based on obviously the priority of the threads that are scheduled. And this is again controlled by RTOS. So there are multiple components that are playing their part together. The SMMU ensures that the memory allocation is appropriate. The RTOS ensures that the memory that is allocated, the processing for them happens appropriately based on the thread priority that is assigned to the threads. And SMMU can also be used to support processing on secure content that is managed outside of the HLOS. Like one example of this is like the data for like fingerprint scanner is stored in a very secured memory region, and that is not accessible to all the applications. So SMMU also ensures that the memory access to a specific region is it allows like accessing of secure memory content only to the registered applications and not to all the applications. So SMMU has a very important role in ensuring that the security is not compromised, and at the same time, multiple applications can continue to use their own respective memory regions or context banks. Yeah, any questions on this?
So, could you explain which type of scheduling algorithm is used for multi-threading? I mean, is it like affinity-based or gang scheduling, or which type of?
That's mainly controlled by the RTOS, and it has evolved over the years. But you can think of it like, so firstly, it is priority-based. So each thread, when you create on the DSP, you will have to assign a priority to it. So based on the thread priority, the scheduler in the RTOS will take a decision. But there can be times when the user does not specify the thread priority. So in that case, the default thread priority is assigned. And if there are multiple threads trying to access the hardware with same thread priority, then it is the scheduling of threads happens in a round robin manner.
Okay, I got it. It means it works similarly like VX works or like that.
I'm sorry, what's VX works?
It is a type of real-time operating system.
Okay. I'm not completely sure of how VX works.
Oh, as you said that if the same priority threads are coming, they are scheduling in a round robin manner. It is also work like that, I think.
Okay.
Thank you.
Yeah, sure. Thank you. Yeah, but for Hexagon, for same thread priorities, they are scheduled in the round robin manner.
Hello.
Yeah. Hello. Yeah.
Yeah. So the addresses for these context banks is it designed statically, or like the or these addresses are like allocated on the fly? Like, because we like said that for each type of application we allocated a different context bank. So basically, if we are doing it statically, then like it could be a performance hindrance, because suppose some application wants to allocate more address, but since we have like statically allocated addresses for different applications, it has to basically go to the disk or some other structure, like from the memory to fetch data or something. So
that is a very good question, actually. Yeah, thank you for asking that. Yes, you are right. So these context banks are first of all allocated statically. This is based this needs to be discussed with the team that owns SMMU, and once, like, let's say if we have a new use case coming up, we have to discuss with the SMMU team to increase or decrease the memory accordingly. That being said, there are use cases when one context bank might not be sufficient for the processing, or there might be a chance that the application needs more memory than that is available in the context bank of a specific application. In that case, the application has the ability to request for a new context bank. There are some reserved context banks that are that are kept separate for like ad hoc usage, I can say, and SMMU can allocate these based on appropriate permissions. Again, like if the application has appropriate permissions, then it can on the fly allocate a new context bank if the memory is not available for a particular application.
Okay. And just one more thing. So in the previous slide, you told that we basically directly stream the data from the camera sensor to this L2 cache.
Right.
So my question is, the camera sensor, the data which is coming from the sensor it's in like a stream manner. So like there is no address mapping to the data which is coming from this camera sensor. So how basically the data knows like where it has to be stored in this L2 cache.
So the data will not be actually stored anywhere. Like it is directly streamed into the L2 cache. So there is no need of like storing the data in the DDR memory itself. But yeah, the data passing from the sensor to the L2 cache happens from in the form of like circular buffers.
So like yeah, but even if the data is getting stored in the L2 cache, there has to be some address mapping, right? Like so without it, that it cannot be possible. Because so
could you please elaborate a little bit more on your question?
The point I'm trying to make is like suppose we are basically getting data in an AXI stream fashion. So there is not like any memory mapped or AXI light protocol. We're basically getting data like the camera sensor is the channel between the sensor and the L2 cache currently is an AXI channel, AXI stream channel.
Right.
So how in this AXI stream channel we can basically map a data to the a particular address in the L2 cache, because there is no address communication happening between camera sensor and L2 cache. There is only this data exchange between camera sensor and L2 cache. So
okay. So I think yeah, that's not highlighted. So there are two paths to it. One is obviously the control path. So if you see, like I mentioned about the control registers, in these control registers, we also pass the L2 address or the cache address where the data needs to be actually streamed. So the control registers will take care of getting the ensuring that the data comes appropriately into the L2 cache, and there is obviously no need of doing any kind of memory mapping in this particular scenario, because we are getting the data into the cache memory, and this operation is actually done almost in a real-time fashion. It is like really fast. Like the data keeps coming like in the form of a streaming format, and then the data is processed and eventually it is sent to the camera ISP. Once the data reaches the camera ISP, that is where a decision will be taken whether it needs to be stored in the DDR or there needs to be some more work that needs to be done on it.
Okay. And just another question. So where exactly these circular buffers are located in this channel? So
they are okay, so they are available in the L2 cache only. Like these circular buffers are like available in the L2 cache only, but camera sensor has access to the L2 cache directly. So that's why the data gets streamed into those circular buffers. It's a kind of a like it's a control mechanism where the buffers are kept here only, but the data that is captured from the sensor is directly streamed into or directly thrown into those circular buffers. And a particular register is programmed to tell DSP that the data streaming is complete and the data processing can begin. Once the data processing is complete, there is another control register that will trigger to the camera ISP that the data is ready to be picked up from a specific memory, from a specific L2 address into the camera ISP. And there are like multiple circular buffers in the L2 cache, which keep, which help in the, which basically ensure that the synchronization is maintained and the data is coming in, processed, and then given out to the camera image signal processor.
Okay, so basically the DSP and the camera system is basically working at different frequencies. So
No, the camera sensor will work at the same frequency as DSP. The camera ISP can work on different frequency. Yeah, that's right. It's possible.
Okay.
Okay. Yeah, another interesting system feature that I want to talk about is the one-way coherency. So the DSP data bus writes, or basically it invalidates the CPU caches. What that means is like there is a dedicated memory controller, which like that this controls the DSP data bus, and it is responsible for invalidation of the CPU caches. This ensures multiple things in the same time. The first thing is that the cache maintenance, the cache flush and invalidation operations on the CPU are not needed, because the DSP data, like the memory controller is directly invalidating the CPU caches once the data is read appropriately. The second advantage is that the DSP side requires cache maintenance, but this is handled transparently by the fast RPC software layer that I told you about, that we discussed for the offloading earlier. So the fast RPC protocol, or the fast RPC driver, is responsible for ensuring that the cache maintenance happens appropriately. So an end user need not worry about the to ensure that the caches are coherent in nature. Another important feature that I want to discuss over here is the quality of service. So DSP, as I mentioned, has multiple real-time clients, which include like audio applications, camera applications, and CV applications. Now, imaging algorithms can consume large amount of data, which require a lot of bandwidth, and it can cause congestion for the other clients. Like the data requirement for imaging algorithms is obviously higher when you compare it to any audio application. So this can like hog the network bandwidth or the bandwidth of the bus, and hence it can lead to congestion. Now, to avoid that, what the hardware does is something called as L2 soft partitioning. Okay, so L2 can be soft partitioned into regions that are assigned to different hardware threads. And why this soft partitioning is associated with different hardware threads, there's a specific reason for this. Let's say a thread, if it gets stalled, it will have a corresponding L2 memory region that will be allocated to that will be allocated in the L2 cache. Now, if the thread is stalled, the L2 cache is unnecessarily being wasted. So that is the reason why we call this as soft partitioning and not hard partitioning, because the hardware will allocate the clock cycles to the remaining threads, because the one of the threads is stalled and it is waiting on data to come from the memory region, and the other three threads will get the clock cycles allocated. And in that scenario, what happens is the soft partitioning of L2 also goes away, and the L2 cache is available for the remaining three threads to be used. So this is like a very interesting and important feature that again helps in optimal performance. There are two more things that are available on the from the hardware perspective. The first one is called internal QoS, which is basically hardware-based prioritization of memory requests. And as I mentioned earlier, somebody also asked this question about the what is the scheduling algorithm. So hardware will just prioritize the memory request, but software or the RTOS, to be more specific, is responsible for assigning the threads to the software threads based on their priorities. The external QoS specifies the system-level hardware algorithms that can throttle DSP traffic to ensure there is optimal performance. So apart from the RTOS taking into account the quality of service, there are some system-level hardware algorithms also that can change the clock cycle or the bandwidth of the bus to ensure that the system is performing ideally. And it's like one example for this can be like when your phone heats up, you might have seen that a lot of functions, they start to stop working. Like there are a lot of functions that will not work when the phone is like in a very heated up state. So that is where the system level hardware algorithms come into picture, and they ensure that the like the power manager will trigger to the system level hardware algorithms that they need to reduce the frequencies and the data transfer rate so that the temperature can be brought down. And once that is done, that's when the performance comes into like its normal mode. So yeah, any questions on this? Okay. So yeah, I think we covered all the important points of the HVX architecture. Just to recap it quickly, we discussed about the domain-specific architecture, why HVX is suited for imaging applications, how its 128-bit SIMD mode along with the VLIW architecture helps in processing large chunks of data. We also discussed about thread-level parallelism and the coexistence of scalar and vector threads. We discussed about the primary L2 cache that is available, which is large in size for imaging data. We discussed about the familiar programming model, the support for SIMD plus multi-threading, cache coherency, easier programming due to LLVM compiler in C++ and Intrinsics. There is support already available for the pre-optimized like maths libraries, computer vision library, or the neural network libraries for most of the common functions. And at last, we talked about some hardware features that allow simplified data processing from the camera pipeline to and from. So we talked about the camera streaming interface. We discussed about shared memory mapping unit. We discussed about one-way coherency and the system and internal QoS. So any questions on any of these topics? Yeah, please let me know. Okay, then we'll move to performance. Okay, so here we have some interesting data to demonstrate both power as well as the performance of the DSP. So over here, we have taken into account some imaging and computer vision kernel benchmarks. So the comparison, as I mentioned earlier, the DSP running on HVX is compared with a quad-core Crate CPU with full neon optimizations. The quad-core Crate CPU is clocked for this experimentation at 2.65 gigahertz, whereas DSP with HVX is clocked at 725 megahertz. For power computation, we are taking into account only the DSP power. The core power is excluding the data bus power or the DDR power. All those powers are actually excluded, and only the power requirements of the chipsets are like respective processors is taken into account over here. So if here you can see like this graph tells about the performance in terms of like cycles taken to execute a kernel, and 1x is the performance of the quad-core ARM CPU, whereas the bars that you can see are the performance of the HVX architecture. So we have like a lot of imaging kernels like Canny, Morph Closing, Fast9, Harris Corner, and most of them are beating the performance, or they are almost at par with the performance that we get on the CPU. So overall, we can say that it is 1 to 3 times faster when we compare the performance of the kernel execution on HVX versus Neon architecture. But when we come to power, the results are even more amazing. The energy per pixel reduction of DSP versus quad-core CPU, if you see here for the same set of kernels that we are executing on the left side, on the right side, you can see that we are getting like 4 to 18 times lesser energy requirement, or the energy taken up is like much lesser when we compare the respective architectures. So this itself is like a testimony, like these two things are a good testimony of why a lot of applications related to imaging, machine learning, multimedia are executed on the DSP, and that is a preferred mode of execution. The sensors are also heavily reliant on the Hexagon DSP because of the power requirement of of the DSP. You can have like always on kind of applications running in your phone, and the like still your battery will not be completely used or hogged upon by the processor. It will be available for a substantial usage. Okay, so the previous graph was talking about individual kernels, whereas this graph talks about like a full-fledged application, like an end-to-end application. So in the previous slides, or in the beginning of my presentation, if you remember, I spoke about low light image and video enhancement. So we do have a low light video enhancement algorithm that runs on HVX. And as you can see, like the performance of the algorithm on the DSP is 3 times faster, and the energy requirement is like 10 times lower. So for the same amount of work that you are doing, firstly, it is faster. Secondly, the the energy requirements are like much lower, and that is primarily the reason why we are able to get always on kind of applications to run on the DSP significantly. Any question on the performance metrics? Okay. Yeah, so I think I'm reaching towards the end part of my presentation. So this is one more interesting slide that I had to discuss about the DSP versus CPU power. And so this graph actually talks about what is the like how the power is spent whenever a typical imaging application runs. So if you see like 7%, like the clock to power up the oscillator, 10% of the energy is spent. 1% goes into some leakages. The L2 flip-flops or the memory related operations, they take around 14% of the memory, and the core logic takes like 7% of the memory. The remaining 68% goes into the HVX processing. So whenever we are running any of our algorithms, in terms of energy computation, like 68% of the work is being done for the energy that is being consumed by the HVX processor or the coprocessor. And again, going back to why we have power savings on the DSP, like I want to just reiterate or add some more points to what I've already discussed. So the CPU is out of order and superscalar in nature, which basically means like any instruction can be executed in any order on the CPU. So that is definitely an advantage when you want to do control code kind of an operation, but it's a big disadvantage when you want to do like intensive processing, which is where like in order VLIW processing comes into picture, and it helps in better performance of the applications, because everything happens in the same order as the assembler has programmed in the assembly. So there's no change that happens, and because of that, the in-order processing of the instructions and the VLIW architecture, the performance is like really good. And no time or no energy is spent in reordering of the instructions, which is spent in the out of order superscalar processing kind of a method. The CPU vector size, as I showed you earlier, is like 128-bit. So like this is again like a problem, because to power on the Neon architecture and just to load 128 bits of memory, it will have like a very significantly high overhead. But the vectors on the DSP are much longer in length, and they can accommodate like a lot of data, and because of that, you get like lesser overhead in terms of power for longer vectors. For CPU, both L1 and L2 caches are used for image processing, whereas on the DSP, the L2 can be actually turned off whenever we are doing, sorry, the L1 can be turned off and only L2 cache can be used. Thus, again, it helps in saving power. And this is again a design choice, like the design choice of CPU architecture. Like the CPU is designed for high megahertz and high clock power overheads, which eventually leads to like higher leakage. But the design of DSP is meant for low power and lower megahertz, which in turn reduces the overheads and the leakages. So this is like a fine-grained overview of why DSP is able to save like power on top of the CPU and why it is preferred.
Hello.
Yeah. Hello, go ahead.
Yeah. So at the end, like we are trying to increase the data level parallelism by using the DSP architecture. So why we not go with GPU or some with GPUs or something?
I mean, you can use GPUs, but again, the power requirements of GPUs are much more higher. So the idea is that in case of DSP, you just have 4 hardware threads, but GPUs will have like 64 or like 128 hardware threads. So the amount of power needed to power on those hardware threads will be significantly higher. And like most of the, like, this is again based on my understanding, I could be wrong here, but like the architectures that I have studied, like for example CUDA, I observed that the computational libraries that they have written, they do like element wise processing. So they they don't rely on vector based processing, but they do like mostly element based processing across multiple threads, and that's what helps in improving the performance. But again, it drains out the battery heavily. The same is applicable for the any general purpose GPU. So GPUs are good at doing like rendering kind of work, but for doing imaging for imaging applications, you need to process like large chunks of data, and HVX is like more preferred over GPUs, mainly because of the power reason. Like the power requirement is much higher for the GPU versus the DSP.
Okay. All right. Thank you.
And you can't run one more thing that came to my mind is you cannot run like always on kind of applications on the GPU, whereas you can do that easily on the DSP.
But like both are Turing complete, I believe. So like
Yeah, they are, but I mean, yeah, it's basically like tuned for a separate use case. Like GPU is mainly meant for use cases which are of short duration, and they need like very high computation. Whereas DSPs are meant for applications which tend to last longer on the time scale, and they would again need significantly higher computational power. So it's again like an application to it depends on the application that you want to use it for. Like the camera is used for a significantly higher time as compared to playing a game these days. So it's more important to optimize the camera pipeline versus the games which get executed, like which basically use the GPUs to a significant extent. So it's a trade-off, basically, I can say, and it is a design choice that is made to ensure that the battery power does not get drained out significantly.
okay. Okay. Thank you. All right.
Yeah. Thank you. Okay, so yeah, I think I'll come to the one of the last slide of my presentation. So this is going to be another subsequent session regarding the Hexagon SDK, which is available for the Hexagon hardware. So on the left side, you can see like there are a lot of tools that are available. The compiler is available. We have assembler. There are specific build modules. There is profiler, resource analyzer, and debugging related tools from the compiler perspective. There are optimized HPX libraries that are available in the SDK, which can be loaded in dynamic or statically. There is computer vision HVX library, which I already mentioned. There are some utility libraries which help in, again, performance comparison, or just simple things like printing your messages appropriately on the DSP. There are examples that talk about, or there is a dedicated like section in the Hexagon SDK which explains about the RTOS of the DSP. There are a lot of examples in the Hexagon SDK, spanning from imaging, computer vision, camera, mathematical libraries. So yeah, it explains about different examples, and these examples make use of the dynamic APIs, like a top level Android APIs, or it can also make use of the fast RPC to allow interaction between the HLOS and the DSP. So all in all, the Hexagon SDK will give you an overview of how to use Hexagon from a developer perspective. And there is a hands-on that is also planned based on the Hexagon SDK. So it will be a very interesting session now that you know about the architecture of the Hexagon DSP and what in Hexagon DSP is ensuring maximum power versus power and performance. It would be a good idea to attend the next session on Hexagon SDK, which will cover all these aspects in much more detail. And yeah, for more details about Hexagon SDK or downloading it, you can download it from developer.qualcomm.com. Yeah, it has the latest SDK available, and you can get more information about it on our developer website. So last slide is talking about, so these are some of our partners who have used Hexagon DSP, and these are like algorithm developers. They have developed their algorithms on HVX, and then they have like licensed them to OEMs. And by OEMs, I mean original equipment manufacturers, who are like the phone manufacturing companies. So these are some of the companies who have developed their audio, imaging, computer vision, or machine learning applications, and then they have outsourced them or licensed them to the OEM partners that Qualcomm has. And yeah, it's been pretty good experience by introducing HVX to the external customers, and we've seen a lot of support. So yeah, we would encourage the student community also to engage with us, and if there's any support that is needed with respect to tools, any kind of offline support that is needed, yeah, we'll be there to help you out. You can reach out to any one of us in the Qualcomm team, and yeah, we'll be happy to assist you with any of your requirements. So with that, I think, yeah, I'll close my presentation, and I would like to thank everyone for joining the presentation. If there are any more questions, I'll be happy to answer them.
I have like not directly related to the content. So like, is Qualcomm is like also like working on developing its own GPUs for low power devices or something? So
it's not meant for low power as such. No, nothing that I'm aware of as of now. Yeah.
okay.
I think is Ravi on the call. Ravi, are you there on the call?
Yeah, Abhikrant. Okay, so
take that question.
Right, yeah. Qualcomm has its own GPUs. It's branded as Adreno GPU. I mean, the GPUs that are used in the mobile phones that have Snapdragon chipsets, they have Qualcomm's own GPU. It's called Adreno. Okay, but to other question, like low power GPU, that's not low power, like compared to at least Hexagon HVX, it's not a low power. Like GPUs generally tend to take high power for the computation.
So like if GPU is already present in the chipset, so like why there is a separate requirement for DSP? Like because anyways the power will be consumed, like GPU.
No, GPU, the power will be consumed only if something gets executed on the GPU, right? Like for example, when you're doing a camera processing, an application that needs camera processing, as Abhikrant mentioned, GPU gets turned off. Like it's only the DSP that processes the incoming frames.
Okay. Okay.
It's not always necessary to have all the hardware blocks to be active. So it's only the ones that do the computation, they remain active. Others will be turned off.
Okay. So yes. Okay. So yeah, it makes sense to reduce power. Okay. Thank you.
Yeah, I think since we have limited battery size in the smartphone, and more and more use cases, they have been moving towards the smartphone ecosystem. it becomes all the more important to consume as less power as possible. Like for our traditional GPUs that are available in our laptops, we don't really care about the power because they are always connected to a power source. But that's not the case with smartphones. So that's why measuring and ensuring that we are getting like maximum throughput or maximum performance at minimum cost of power becomes like extremely important when we talk about the mobile ecosystem. And we cannot have like applications which just drain out the battery like in just 5 minutes of usage. Like that kind of an application will not be preferred. So that is why we tend to take a trade-off between the GPU and the DSP to get like the optimal performance versus the optimal power consumption also, so that the battery is not drained out completely.
Okay, thank you.
I have a general question about digital signal processors. Is that okay or?
Yeah, sure. Go ahead.
So the presence of an RTOS, is that mandatory, or is it like do there exist DSPs that do not really have an operating system but just have, I don't know, like
Yeah, that is like there are DSPs that don't have an RTOS in them, but the reason to have an RTOS is that it ensures that the programming model is familiar for someone who is coming from an x86 or an ARM architecture. So you wouldn't have to make a lot of changes to your multi-threading logic because the support for p-threads or very generic kind of multi-threading APIs will be available by default if the RTOS is available. If the RTOS isn't available, then the scheduling of threads has to be done like the program by the programmer, and all that has to be done like manually, which becomes like a tedious job for someone who is writing a high-end high-level application. So it's just like an additional feature that is introduced in terms of RTOS so that it makes the life of a higher level application developer easy.
right. So this RTOS, is it I mean, is there a fixed definition of what an RTOS does? So if I just take care of the threading on the hardware, if I have induced some kind of logic to just take care of the threading and not the scheduling, would you still call it an RTOS?
No, I mean RTOS, like it is different from an HLOS basically in a lot of ways. But yeah, the basic idea is that HLOS has more intelligence to queue up processes and to ensure that whatever process is queued up in the pipeline that can be like executed at a later point of time in the time cycle. But in case of RTOS, most of the things, as the name implies, have to happen in real time. So that's why it is a very thin layer OS, which is responsible not just for like it's not just responsible for like thread scheduling, but it also takes care of like interrupts, ISRs. It also takes into account like it interacts with the SMMU. So the RTOS will be the one that is responsible to interact with the memory management unit. So if a user does not have an RTOS on a DSP, then all the memory management, if it's like a coprocessor or if it's like a multiprocessor kind of a system, then all the interactions between different peripherals will have to be taken care of by the programmer, which helps if an RTOS is available. So it's not just limited to the multi-threading aspect, but even interaction with the peripherals becomes extremely easy. You can easily write some device drivers that can that are using the RTOS APIs to do seamless like interaction between multiple processors in a multiprocessor system.
Right. Thanks.
Okay. Any more questions? Okay, I would like to thank everyone for making the session so interactive and asking a lot of questions. So yeah, thank you so much for your participation. And there are 2 more sessions planned after this related to Hexagon. One will be on the Hexagon SDK, and the other one will be on Halide. So yeah, we would love to see you in that in these 2 presentations also. That will also be followed by another hands-on where you can try some experiments on the Hexagon simulator, run some applications, play around with it to get your hands on some of the examples that we provide in the SDK. So yeah, please stay tuned and uh, join that session if you are interested. Yeah, thank you. Thank you so much.
Abhikrant, I had one small thing. So
Sure.
for the hands-on session, if there are some tools that the students can already install so that it's easier to do the hands-on, can you share the links with us?
Sure,
is it
sure, sir.
possible?
Yeah, sure. I'll discuss with my respective teammates and I'll share it to you, sir. Yeah.
Yeah, that would be awesome because we'll post it up and then the students can already have it installed so that it's easier to they can even try
Makes
out
sense.
things.
Makes sense. Yeah. Okay.
Thanks, Abhikrant, for a beautiful session. So it was a really nice session. I think the students also enjoyed it a lot, and we are all looking forward to the following sessions for this.
Thank you, sir.
Thanks for the talk, and we hope we'll have more interactions in the future.
Definitely, sir. Yeah, definitely. Thank you so much. Yeah.